Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, good morning. So I'm very excited to be here and tell you about some very new research. This research was completed about 4 weeks ago, so this is the very first time I'm talking about it in public. So consider yourself very lucky, because this is very exciting for me. So I'm a postdoc at Microsoft Research New England. This research is done in collaboration with a number of colleagues. Jeff Lupin is a developer at New England R&D. Pete Hammond and Jennifer Rexford are networking researchers from Princeton. And Michael Shapira is a postdoc at Yale and Berkeley who works on theory, networking, and game theory. So what we're going to talk about today is some issues relating to the security of the internet. And so before we start talking about security, let's have a look at what the internet looks like. So the view of the internet we're going to use in this talk, we're going to look at it at the level of autonomous system. So each one of these purple nodes here is an autonomous system. That's a huge network related to a single company. So for example, Microsoft has a few autonomous systems that it runs. You can think of AT&T's network as a single autonomous system. A university might have its own autonomous system. So in all of this talk, we're going to focus on autonomous systems as our nodes. And we're going to look at graphs of these nodes and look at routing across these graphs. Okay? So the way internet routing works is basically there's these IP addresses that everyone in the world wants to reach. So for instance, if you want to watch videos on YouTube, you go to the IP address related to YouTube, and you get your traffic from there. You get your videos from there. So what would happen here, the autonomous system that serves the YouTube videos has an IP address. It'll advertise it to the world. The world will set up routes to that IP address and route its traffic that way. So for example, these autonomous systems, which are small customers of Pakistan Telecom, would send their traffic to Pakistan Telecom, which would then forward it on through the internet to YouTube and reach the videos. Okay, so I picked these particular networks for a very good reason. A couple of years ago, we had a very interesting attack that happened. Sorry, it wasn't an attack. It was more of an incident or a misconfiguration that occurred. So what happened was Pakistan Telecom actually hijacked the traffic that was supposed to go to YouTube. So we actually have this memo that came from the Pakistani government to the ISPs in Pakistan saying, please censor this URL over here. Here are the IP addresses associated with that URL. So that's how you reach that URL. And they required these networks to stop traffic from inside Pakistan to reach these networks, to reach these addresses. So if we look at our graph here, what really should have happened is that Pakistan Telecom should have been dropping all the packets that were destined to YouTube. So if a packet said, I'm going to YouTube, just drop it and don't let it go to YouTube. But here's what they actually did. They ended up telling the world that they were YouTube. Okay, so this was a misconfiguration. If they had done this internally in their own network, it would have worked. But what happened was it leaked to the outside world. The outside world saw this address and decided to route their traffic to YouTube. And so actually, YouTube went down for a couple of hours while the operators were on the phone calling each other, trying to figure out what happened and how to fix it. So we had this outage for about 2 hours where no one could reach YouTube. So these are the flavors of the attacks that I'm going to be focused on in this talk. And what I want to do is, as we've seen, there are serious issues with the routing system that we use today. I want to tell you a little bit about these issues. We've known about these issues for about 15 years. There's been a decade of research trying to deal with these issues. And all of the protocols that we've come up with over time, none of them have actually been deployed. There's a lot of good reasons for that. But what we wanted to do in this research was, rather than design a new secure routing protocol, look at the things that other people have done over the years and try to figure out which one is the right one to deploy in the system. So what we're going to do is just compare these routing protocols. The way we did this in this work was we did it using simulation. So we had data about what the internet looks like. There are researchers who actually work on figuring out what the autonomous system level of the internet looks like. So mapping out these networks. We took this data and we ran simulations on what attacks might look like to see how effective these different security protocols are at preventing these attacks. Okay, so if you know nothing about networks or nothing about how the inter-domain routing system works, don't worry about that. We're going to go over that first. So I'm going to go over how internet routing works, why economics matters in internet routing. This is not your standard shortest path routing sort of intuitively think about when we think about networks. After that, I'm going to talk a little bit about the different secure routing protocols that people have developed over the years and some of the attacks that you can actually launch against those protocols. And finally, I'm going to go over some of the implications of our results and what they mean for the right kind of secure routing protocol to actually work to deploying in the system. So the first part is going to be very brief. I'm going to spend most of my time on part 3, and then part 4 will be very short. OK, so the routing protocol that controls the internet right now that we actually have deployed is called BGP, the Border Gateway Protocol. It's a 3-letter acronym. But what it actually does is it sets up paths from autonomous systems, so from these purple networks, to destination IP addresses. So basically for every address, we're going to set up paths from all these networks to that IP address. So for instance, for YouTube, we would set up paths to that destination address. For the rest of this talk, I'm going to use this network, so we're going to become very familiar with it. This is the IP prefix. This is the destination that everybody, all of these networks, would like to reach for this example that we're going to talk about. Okay, so like I said, routing in the internet is not just shortest path routing, not what we're used to when we think of just trying to find the shortest path from one node to another. These networks are economic entities. So they actually have business relationships between them. And these business relationships are going to determine how routing happens. So when we model these networks, they're quite complicated. But the model that we're going to use in this talk is that there are different kinds of relationships between these networks. So the first relationship I'm showing is a customer-provider relationship. So this might be, for example, a university might be paying a provider like AT&T for service, for routing services. And so what these arrows mean in this graph is that money is flowing from the customer to the provider. So right here I've got 3 customer-provider relationships. 20984 is a customer of AT&T, and so on. So these are customers. This is a customer of that one. Okay, so the other type of relationship that you have in this network is called a peer-to-peer relationship. So peer-to-peer means there are 2 networks that are about sending equal amounts of traffic to each other. So because they're sending about equal amounts of traffic, they're not going to charge each other for services. It's just cheaper rather than keeping track. So in this network, I have 2 peer-to-peer relationships. AT&T is a peer of UPC, which is a broadband service provider in Europe. And there's UPC and Init7, which are also peers. Okay, so this is our network. And how does routing actually happen? So remember, all these networks are trying to reach this particular destination IP address. So this destination IP address belongs to this network UPC. And so what UPC is going to do is going to tell the world, if you'd like to reach this prefix, please send your traffic to me. So the message basically says, I'm UPC, and here's the prefix you'd like to reach. Okay? So these 2 networks will forward their traffic to UPC. And what the routing protocol does, it's called a path vector protocol, which means that each node announces the path that they're using to the destination. So very simply, when Init7 sends his announcement to 432.84, he's going to put his name in the path, put UPC in the path, and put the prefix in the path. So we just set up these path vectors. So when we get to 209.84, he's going to have 2 announcements, one from AT&T and one from 432.84. Again, each one of these is a path. And he needs to choose a path. So how's he going to choose a path? So our model is going to say that he's going to prefer the cheaper path. And then if he doesn't have a cheaper path, he'll just prefer the shorter path. In this case, both of these paths are through his providers. He has to pay for both paths. So basically, they're equal in terms of cost, at least in the model we're going to use. And so how is he going to make his choice? He's going to choose based on path length. And so the shorter path is through AT&T, and he's going to route that way. Okay, so one thing you should notice about this is when a node makes an announcement, a routing announcement, it's like a commitment to carrying traffic. So if I announce a path to someone, it means I'm willing to carry your traffic. So the next question I want to ask is 209.84 ever going to make an announcement to 432.84? Okay, so if he made that announcement, it's like a commitment to carrying traffic. And this is actually not going to happen. Okay, and here's the reason. If you look at 209.84, he pays AT&T and he pays 432.84. So if 432.84 was to send traffic like this, 209.84 is paying twice, right? So it's not in his interest to do that. Sort of, if you think about it logically, it's like a small network like University of Washington's network paying Verizon and also paying AT&T, carrying the traffic from AT&T to Verizon. It doesn't make sense. So we don't expect to see this kind of traffic flow on the network. Okay? So basically, that's all I want to say about how these network works. And now we can start talking about attacks and secure routing protocols. And by the way, if you have questions, please feel free to stop me. Okay. So what I'm going to do is I'm going to talk about a very basic kind of attack against the existing system. Then I'm going to talk about a couple of security fixes. There are actually going to be 3 security fixes. And we're going to see how these can and cannot be attacked. Okay? So first of all, the focus of this talk is on traffic attraction attacks. In my opinion, this is one of the most critical attacks that we should think about in these networks. What a traffic attraction attack is there's an attacker that wants to convince the maximum number of nodes or a certain set of nodes in the network to actually route traffic through it. So for example, we could have an attacker here. And what it wants to do is it wants to grab the traffic that's supposed to go to this IP prefix and send it through its own network. So this is similar to what happened between Pakistan Telecom and YouTube. So this would be our Pakistan Telecom. Now, why is this a problem? Well, once this network actually carries the traffic through its own network, it's able to eavesdrop on the traffic if it's unencrypted. And even if it is encrypted, it can decide to drop the traffic, so fail to deliver it altogether to the destination. So once it's got the traffic, it controls it. It can do whatever it wants. And so this is, you can think of this sort of as you can set up your servers, you can make sure your software is secure, you can encrypt everything, but the traffic doesn't arrive because the network doesn't deliver it because somebody hijacked it along the way. Okay? So this is basically what we're going to focus on in this talk. Okay, so how might traffic? All right, so here's what he's going to do. Today's BGP, so today's routing protocol, actually contains no validations. There's no checks. You can't verify any of the information that anyone's telling you. So basically what our attacker's going to do is he's just going to say, UPC is going to claim he owns the prefix, which he does. And the attacker's going to say, actually, I also own the prefix. Right? So now what's going to happen in our network? What's AT&T going to do? Well, first of all, AT&T doesn't know who owns the prefix. He's supposed to learn that from the routing protocol. So he's got these two messages. They look fine to him. Which one is he going to choose? Well, if we look at the business relationships in this network, 20984 is a customer of AT&T, whereas UPC is a peer of AT&T. So that means that AT&T makes money, actually gets money from here, if he routes this way, whereas if he routes this way, he doesn't make any money at all. Right? So what's he going to do? He's going to route down to the attacker, because that way he makes more money. So if we continue through the network, we can see that when we get to init 7, he's got these two announcements. This one's false. It's also longer than this one. This is a one-hop path. This is a two-hop path. But he's going to route downwards because this one is his customer, right? So he's getting paid from 432.84 because he's a customer, whereas here this is a peer-to-peer relationship. No money is going to flow. So he makes more money if he routes downwards. Okay, so our attacker has been pretty successful, and this is basically what happened between Pakistan Telecom and YouTube. Okay, so actually ran the simulation on the entire internet graph. So what I'm showing you here is just a small piece of it, so you can get an intuition of what's going on. When we run the simulation over the entire graph, 62% of the internet actually ends up sending its traffic through the attacker. And a lot of that happens because of these customer preferences, because you prefer routing through your customers. Okay, so this seems like pretty egregious attack. Someone's claiming that he owns a prefix that he doesn't own. And so something people have been talking about over the years is preventing this type of behavior. What they're suggesting is, so first of all, I should say that IP addresses in the internet are supposed to be allocated to networks. So each IP address belongs to a single network. It's not like an IP address can belong to many networks. So what they'd like to have is actually a database that's going to have a mapping between IP addresses and the networks that own them. Right? So if we had such a database, then the attack that we saw before when a network announces a prefix that's not actually connected to it wouldn't work, because anybody could check the database and see that that announcement was false. Okay? So the previous attack that we saw is not going to work. So suppose we had such a database. What could our attacker do? So I'm just going to basically try to figure out what's the smartest attack he could do. Suppose he wants to announce the shortest path he can get away with to as many neighbors as possible. So what's the shortest path he can get away with? Well, nobody knows that this path here doesn't exist in the network, right? So the path from the attacker to UPC. So he's just going to claim, actually, I'm connected to UPC. Everyone knows the prefix is connected to UPC. Now the attacker claims he's connected to UPC. And when we look at AT&T's decision, he's still making more money if he routes downwards towards the attacker versus to UPC, which he doesn't make any money at all, right? So what AT&T is going to decide, even though this path is longer and it's false, he doesn't know that, and he's just going to send his traffic to the attacker. Okay? So, and again, if we continue through the network, the same thing is going to happen. So I just wanted to talk a little bit about why this is actually useful. Most of the attacks we see in practice are just misconfigurations, which means that someone types in the wrong IP address in the router and starts announcing something that they shouldn't be announcing. And that actually does happen. The most egregious time that we know of was the YouTube issue, because everybody uses YouTube, so everybody saw that this happened. But what I'm talking about in this talk is actually malicious attacks. So this guy is actually trying to game the protocol and trying to attract as much traffic as he can. Okay? So even if we had this, we'd be stopping a lot of misconfigurations, but definitely not malicious attacks if the attacker was a little bit more clever. Okay? So clearly there's something wrong here. This guy's announcing a path that doesn't exist in the network. So the next secure protocol we're going to look at is one that's going to prevent people from announcing paths that aren't really there. Okay? Oh, sorry. OK. So actually, I ran the simulation on the whole network. 58% of the internet is going to route through the attacker. So the path is a little bit longer. Before, it was 62% routing through the attacker. This time, it's 58% routing through the attacker. So we can see that origin authentication really hasn't helped us much in preventing this attack or reducing the impact of this attack, at least for this particular network. OK. So the next security mechanism we're going to look at has to do with preventing people from announcing paths that are not really there. Okay, so this mechanism, first, it has origin authentication. So it has this database that maps IP addresses to the networks that actually own them. But it also has this additional mechanism that prevents people from announcing paths that don't exist in the network. So for those of you who are familiar with cryptography and are interested in how exactly this protocol works, then please pay attention for the next minute. For those of you who are not, if you don't get this, it doesn't matter for the rest of the talk. Bottom line is what this protocol is going to do is it's going to prevent anyone from announcing a path that's not really there. Okay, so let's see how it works. This protocol uses something called public key signatures. So this is a cryptographic tool that works in the following way. So suppose UPC wants to send a message. What he's going to do is he's going to sign that message. In addition to signing the message, there's going to be some kind of public key. So a public key that's going to be known to everyone. So everyone who has the public key and the message can verify it came from UPC. So you can authenticate the message came from the right person. So nobody can claim something in someone else's name. Okay? So what we're going to do is we're going to set up a public keys. Each one of the nodes in the network is going to have a public key. And now our database is also going to store the public keys as well. Okay, so we have to set up this entire infrastructure, which is kind of difficult, and we can talk a little bit about why that's difficult. But suppose each one of these nodes has public keys. The routing messages are going to change. Basically, they're going to be authenticated messages. So before, UPC announced the path to the prefix, but now he's going to do the same thing, and he's going to sign the message with his public key. That means anyone in the network can go to the database, look up the public key of UPC, and verify that this message came from UPC and not from anyone else. Okay? So the routing protocol is going to proceed in the same way. But now every time someone announces a path, they're going to sign it with their key, so that verifies that they're the one that said it, and then also include the message from the previous guy. So now you can check that every node along the path actually announced the path that you're seeing. Right? Nobody can make up paths because every node on the path is going to sign that this is really the path that they're using. So as you can see, this sort of goes on. If we had a 3-hop path over here, then this path would be signed by the orange key of 432.84, the purple key of init7, and then the yellow key of UPC. Right? So we just have these signed paths, and now you can verify that every path that you see is really there. Okay. So that's it for the cryptography. The only thing I want to mention is that this is a protocol that's inline, which means that routing messages need to be signed on the fly. You need to use public keys to do this. This is actually pretty slow. So it's not just like sending a message. You're actually doing quite a lot of computation in order to form these messages. So that's one of the issues with this protocol. But anyway, that's how it works. So now let's suppose we live in a world where we have such a protocol, and it's actually deployed. Today we don't have this. We're actually working towards this. OK, so now for those who didn't understand, come back. So what's our attacker going to do? OK, forget that. Sorry. OK, so what's our attacker going to do? OK, again, he wants to announce the shortest path he can get away with to all his neighbors. So he can no longer make up paths, because this protocol is preventing him from doing that. So he's got to choose paths that are actually there. So this particular node has 2 edges. That means he's got 2 paths he can choose from. So let's suppose he picks the shortest one. OK, this path through AT&T. So he's just going to take that path, and he's going to announce it. And he's going to do everything properly. He's going to sign the message correctly with his own red key. This looks like a normal secure BGP message. Everything verifies. Everything checks out. It's a correct message. Right? And he announces that to 432.84. And remember that that's a commitment to carry traffic. So 432.84 now has the right to either route through init7, which has this 2-hop path over here, or through 209.84, which has this 3-hop path. So again, let's look at the business relationships. Which way does he make more money? So if he routed this way, he has to pay, or if he routed that way, he makes money. So we can see what's going to happen. He's actually going to route down to the attacker, even though the path is longer. This is a legitimate path. It verifies. Okay? So same thing happens with init7. He now has these 2 choices. He has this 1-hop path through UPC, and he's got this long path all the way around the network in which he actually makes money. So again, he's going to route through 432.84, and all this traffic is flowing through the attacker. Okay? So some of you, OK, so first of all, when this happens, 16% of the internet actually ends up routing through the attacker. So this is lower than before. We saw 58% before. The reason it's lower is because the path is longer. So there are nodes somewhere far away in the network that will see this long path and will say, actually, you know what? I don't want to use this path. It's too long. Let me use the actual other path, which really does end up going through UPC. So there are a lot of other nodes that you're not seeing here. But anyway, this is the outcome that we see. OK? So some of you might wonder why this is an attack. Nobody's asked that, but I will talk later about why this is an attack, because it seems odd. He's sending messages that are legitimate, and they're signed, and everything's fine. We'll talk about that in a second. Before we do that, I want to talk about the strategy that our attacker used. Okay, so is this actually the best strategy that the attacker can use in this network? So let me tell you about why you might think this is the best strategy and why sort of every paper that I've read prior to the research that I started doing with my colleagues on this thought that this was the best attack strategy. So if you saw how routing works, basically nodes make their decisions based on their business relationships with their neighbors. So an attacker can't lie to its neighbors about what their business relationships are, because neighbors know that. They signed a contract. The neighbor knows who he's paying and who he's not paying and who's paying him, right? So you can't lie about that. So the next thing that a node makes its decision on is on path length, right? So first, business relationship, who am I sending it to? And then how long is the path that I'm using? So since the attacker can't lie about the business relationships, he might as well just announce the shortest path he can get away with. Right? That seems like it makes sense. And so that's why I talked about this sort of attack strategy of announcing the shortest path he can get away with to as many neighbors as possible. Okay? So it turns out that this is actually not the best strategy. Okay? So it turns out that, in fact, sometimes announcing longer paths is actually better than announcing shorter paths. Okay? So you might think that because nodes sort of make their decisions on path length as well as business relationship, short paths should be the best thing to do. But actually, we have examples, and I'm going to show you one where longer paths are actually better. The other thing that I talked about earlier was how making a path announcement is a commitment to carry traffic. So if your goal in life is to carry the maximum amount of traffic, it seems logical that you should announce paths to as many people as possible, right? If you announce to fewer people are going to route through you, right? That's what you would think, but actually that's not true. We have also examples that we found in the data that sometimes announcing to fewer people is better than announcing to more. And this is just because of the complexity of how this routing system works. So all of these results, so for those of you who are interested in NP completeness and things like that, if not, don't worry about this. Actually, it turns out that finding the optimal attack, so that if you're the attacker and you want to figure out the way to attract the maximum amount of traffic to your network, that's actually intractable. It's computationally hard to do. And it turns out that sometimes the best attack looks really strange. And I'll show you that in a second. So the bottom line is, for our research, this means that we're going to run simulations. We don't know what the best attack is. So we're just going to pick a specific attack, which is this one over here that I've been talking about the whole time, simulate that, and compare protocols based on that. Okay? So, so there are questions here? Yep.
Could the attacker use more like a longer prefix to hijack the traffic?
Yes. Okay, good. So I didn't want to talk about this in this talk. It's called a sub-prefix hijack, which I'll talk about afterwards, after I finish. Okay? So he could do that, but we didn't consider that because basically sub-prefix hijack attracts 100% of the traffic in the internet. So it's really not interesting. There's nothing to discuss, right? So, okay. Anything else here? Okay, great. So I bet you are all excited to see why longer paths are better than short paths. So this was, for me, one of the most exciting examples that we found in the data. So let's look at our attacker. Before we had him announce the path through AT&T, that was a 2-hop path. Okay? Now I'm going to have him announce a longer path, which is a 3-hop path. Okay, so he's just going to do exactly the same thing he did before. Instead of sending traffic, instead of making the announcement in this direction, he's going to announce it in this direction. Again, this is just a correctly formed cryptographic announcement, and he's going to send it. And AT&T, again, is going to route through the attacker because he's his customer. Okay? Bottom line is, when you run the simulation, 56% of the internet is routing through this attacker. Okay, that's compared to 16% when we had him announce the shorter path. And it's actually almost as much as what he would have gotten if he had announced he was directly connected to the IP prefix. So one of the things that I wanted to mention, sorry. Okay, so any guesses on why that happens? Okay, so this is kind of amazing to me because the attack that everyone thought would be the worst one, which is just claiming you're directly connected to the prefix, just announcing a long path that actually is there to the prefix is almost as effective. The reason for that is AT&T is a big network. Okay? So in this outcome, when he announces paths like this, he's attracting traffic from this huge network that has 500 customers. If he was to try to get the traffic from this side and route it this way, he's only getting this guy who has 4 customers. Right? So he's not very good to get. The goal is to get AT&T to route through you, and that's going to get you most of the traffic. So 56% versus 60%. Okay, and so the bottom line is one of the key observations in this work is that who you announce to is actually as important as what you announce. And the reason this is interesting is because secure routing protocols basically focused on making sure people don't lie about paths, don't make up short paths that aren't there, don't claim to be connected to things that they're not. That's been the focus of most of the research on secure routing. But what we found in this work is that who you talk to is actually as important as what you tell them. So here the path was so long, but it didn't matter because this guy is still a customer and he's still preferred. He just route this way, and the traffic goes to him. OK, so some of you might be wondering, again, is this an attack? So I don't want to claim that this is or isn't an attack. The bottom line is it's pretty effective. So if your goal is to attract traffic, you have been very effective in doing it by doing this operation on secure BGP. So one of the reasons that you might think this is an attack is because we said that a node should only carry traffic if it earns him money. Right? So this particular guy here is called a stub. So a stub is a node that only has, that doesn't have any customers. Okay? So a node that has no customers, basically, if we look at what this guy's doing, he's paying out on this edge to AT&T. He's paying out on that edge to 432.84. So if this guy was rational, he would never route his traffic this way. Because he's interested in attracting traffic, he's behaving strangely, and this is what he's doing. Right? So actually, one thing that we can learn is a node or a network that has no customers actually should never be carrying any traffic through its network, except traffic that ends in its own network. So that means if it's an IP address that's connected to this guy, then he should be announcing it to the world, so stuff can terminate at him. Or he can send stuff out to the world. But he should never be carrying stuff through him for the world. Okay? That means that something strange is going on, at least according to this model of how traffic flows in the network. OK, so all is not lost. We have something else. And this is very interesting because this is a sort of security heuristic that's in place today because we have no secure routing protocol in these networks. This is called defensive filtering. Any of you who are familiar with access control lists or ACLs, this is a very similar idea. So basically what you're going to do is you're going to have a network, like a provider. So this guy's a provider of our stub over here. What he's going to do is he's going to keep a list of the IP addresses that are supposed to be connected to this network. Okay? So if he has such a list, he can verify that this guy is announcing prefixes that he actually owns. And if he sees him announcing anything, any path for any prefix that doesn't end at his network, then he'll just cut him off. So for example, what this guy would say is he would check, this prefix is not owned by this stub, right? We know that he should never be carrying traffic this way, and so I'm just out to the correct destination. And that'll actually prevent a lot of attacks. And here's actually the good news. The majority of the nodes in the internet are stubs. So 85% of the nodes in the internet have no customers. And so if we could actually implement this, because those nodes should never be carrying traffic through them, if we could implement this properly, then we would stop a lot of attacks. Okay? So I'm going to talk a little bit more about why this isn't necessarily implemented properly. But before I do that, actually, are there questions here? Okay. So before I do that, I've been talking about one network for most of this talk. I chose it because it's a very interesting network that I can show you everything I want to show you on. But for full disclosure, now what I'm going to do is we're going to choose attackers and victims at random. So I don't want to pick just a single example here. Let's assume that we chose the attacker and victim at random and saw how often the attacker can be successful. So just arbitrarily, let's say an attacker is successful if he convinces 10% of the internet to route through him. I could have done this for any number. I just chose 10% for fun. And because it's a pretty big number, right? So if you're convincing 10% of the internet to go through, you can damage quite a lot of traffic. Okay? So what I'm showing you here is this is BGP. This is what we have in place today with no security. This shows that 88% of attackers can attract at least 10% of the internet to route through them. Okay, so that's pretty high. This is what happens when we add the cryptography. So actually, it drops down to about 12%. So you limit the success of the attacker. The reason is because you force him to be expected, right? The thing that's not to be expected, at least for me, was if we actually add, so let's suppose we're in a world where we only have BGP, so we have no crypto at all. We just have these access control lists, so this defensive filtering where providers prevent their customers from announcing prefixes that they don't own. So if we had such a thing, actually it turns out that the number of attacks drops down to about 14%. So this is 12%, this is 14%. So what's happening is that this defensive filtering mechanism, just this heuristic, is actually almost as effective as the heavy cryptography that we've sort of been working for many years to put in place. And this is sort of what we've been doing in the interim. Over here, I'm showing what happens if you combine both the cryptography and the defensive filtering. So you would prevent stubs from announcing any path through them, even paths that are correctly formed cryptographically, right? So the attack that I showed right at the end couldn't happen. Okay? The reason that these curves look this way is because only 15% of the internet is not a stub. So you can basically take these orange lines and scale them down to 15%, and you get the purple lines. Okay? So that's basically, for me, one of the most interesting results here is that this heuristic is almost as effective as the cryptography. The other thing that I want to briefly mention is we only ran this for a single attack strategy. There could be worse attacks. We just ran it for the one where he announces the shortest path, and I've already shown you that sometimes announcing longer paths is better. Various other weird things are better. So there could be even more dangerous attacks, and so these orange curves could be higher than they actually are. The nice thing about this purple curve is that it stops at 15%. If we cut off all the stubs attacks, we actually have a hard line over here. So it's possible that this is actually higher than this. Okay? I just don't know that because I didn't run every possible attack that could possibly be run for every possible attacker. Okay? So that's what this data is showing you. All right. So questions here? Okay, so I'm almost done. So a little bit more about defensive filtering. So this seems like a great idea. Okay, why don't we just do it? Why aren't we just doing it now? It doesn't require crypto. It doesn't require changing any of the routing messages. Just put an access control list in your routers. So here's why it's hard. It relies on altruism and trust. So first of all, the rest of the internet has to believe that AT&T actually did the defensive filtering. It only works if the provider does it locally. So you can't, if you're far away from this particular stub, you just have to trust that his provider has implemented this. So the other thing is it's sort of the provider has to protect the rest of the internet from attacks by its stubs. Sort of altruistic thing. You have to say, OK, I'm going to be nice and protect the internet from my stubs, so let me filter its messages. The other thing that's a big issue is that maintaining the list of addresses that are owned by these networks is annoying. It's hard. And we don't necessarily know which IP addresses are connected to which networks, which is why we have all these issues. What happened when they were developing the internet was they gave out IP addresses to networks, huge blocks of them, and then people took blocks, sub-blocks, and gave them to other networks and sold them. And so it's not really clear who owns which blocks of the IP address space. But if we had origin authentication, we would actually know this information. So if we had this database that matches networks to the addresses that they own, we could actually use this database to set up these lists and then have defensive filtering implemented in a more robust way than what we have today. So this is actually something I'd like to do. And this is not necessarily, this at least wasn't clear to me before I did this research, that this is something that's important to do. Okay, so the bottom line is with these types of traffic attraction issues, who you tell is as important as what you tell them. And what's interesting is that the majority of routing protocols have focused on constraining the announcements that nodes can make, so making sure you don't lie about paths that don't exist. But this really doesn't constrain who these paths are announced to. And that's one of the major issues with these protocols. So some of the things that Microsoft can do, Microsoft is a huge company. It carries a huge fraction of content in the internet. It actually has a little bit of clout in convincing people to do what it wants. So some things that it can do is push for the deployment of these protocols, for instance, in its own network, secure BGP, defensive filtering, ask its neighbors to implement these things and sort of help things propagate through the network. And the other thing is that's kind of important is make sure that the data centers are well connected. If your data center is in the corner of the internet and there's someone somewhere else who's trying to hijack your traffic, if you're not very well connected, you're more vulnerable. Okay? And actually, Microsoft's data centers are pretty well connected, so that's a good thing. Okay, so that's all I wanted to say. I'm in booth 217. This research just got put up on the Tech Report archive. It's 12/04/28 if you'd like to look it up. Okay, thank you. Questions? Yeah. Oh, okay.
Since we saw that a lot of the attacks were going to cost the attacker money, does that mean that the attacker actually, in the end, has to pay for this, or does it mean like somebody could maliciously make that, or a person who wasn't there could make the company pay?
Okay, to be honest with you, I'm not sure. I'm not sure what would have happened in these situations. The thing to sort of think about and to understand what's happening here is the network, that the guys who own the network are paying for this, and you're sort of imagining a router being hijacked by someone outside or someone who's got a completely different set of interests than the network itself. I don't actually know what would happen in these cases. I'm sorry, I can't answer that.
Hi, thanks for this. This is quite fascinating, actually. There's some research that's been showing, though, that the average AS path length is constant or decreasing, even though the number of ASes is increasing 10% year over year. Is there any relation between that kind of network diameter and the rate of success and traffic attraction in your work?
Okay, I don't know if I can give a rigorous answer to that question. I think one of the reasons that path length is decreasing is there's been a lot of discussion, the increase in the number of peering edges in the internet. I don't know if you saw the New York Times article a couple of days ago about that. Yeah, sorry, this might be. Okay, so what's happening now is that there are these giant sort of content providers like Microsoft or like Google or Facebook or whoever. They're sticking themselves in the network, and they're forcing the creation of peering edges with all these giant networks that they normally wouldn't be able to peer from. It's just the fact that they are, so sort of structurally, if you look at the structure of the internet, these guys should not have peering edges, but the reason they have it is just because so much traffic is flowing through them. So that might be one of the reasons that the diameter is changing, because these networks are so stuck themselves sort of central in the network. So you can think of the internet kind of looks like a clique in the middle with trees growing down, and the trees are about of depth 3. So now what's happening is these data centers are coming in, sticking themselves, and just connecting themselves everywhere, all over this place, without regards to the structure. So that might be one of the reasons that path lengths are shortening, because so many people are going through the peering edges. If people prefer customer paths over peer paths, then that puts those things at risk. The thing is, I'm not sure exactly what everybody does in practice. So what I'm using here is a model of the preferences that people use. This model is based on empirical data that people have inferred that this is what the business relationships are. I would love to meet someone in Microsoft who could tell me what the business relationships are and what the BGP preferences are. So if anyone knows those people, please introduce me. So that's all going to affect these things. So one thing that Microsoft can do is make sure that its neighbors, even though perhaps it has a peering edge with that neighbor, make sure that neighbor prefers to route through it no matter what it sees from elsewhere. So, I mean, that's the best I can do in terms of answering that. The issue of what the business relationships actually are in real life is very difficult to answer because people don't tell us these things as researchers.
Are there security implications in this for end users, or does SSL protect them and it's really just a sort of denial of service type attack we're talking about?
I guess, okay, so SSL will protect confidentiality, which means that people can't read your data. What is happening here is basically denial of service. It's an attack on availability. So even if it's protected with SSL, I'm just dropping your traffic, it's not getting where it's going. So I guess it could have implications on end users if you're concerned with actual availability. The other thing that's interesting is the majority of traffic is not encrypted, right, in the internet. So it's even actually attacks on confidentiality because we don't encrypt traffic end to end usually.
So for all these rules of the for the defensive filtering, so I guess the provider have all these rules for the for its customers, so it goes all the way up to the root?
No, okay, that's a great question. So I don't think I was clear enough about that. Let me just go back. Here's the challenge. Let's just look at init 7, okay? So basically the question that you're asking is, can someone, I need my pointer. If someone is far away from the stub, can it actually implement defensive filtering? That's actually kind of hard. So suppose this guy wanted to do defensive filtering on him. He doesn't trust this guy to do things properly, so he's going to do it himself, right? If he knows that this guy is a customer, this guy over here, like if he knows the business relationships, maybe he can do it. But the problem is the internet's kind of complicated. People don't necessarily know what the business relationships are. So at least as a researcher, when I'm looking at this in sort of a global way, I can't expect someone up here to filter for someone down here. So the real challenge in implementing filtering is have this guy here and this guy here. They both know he's a stub, right? They know what he is. They know where he sits in the internet. So they're the ones who should be doing the filtering. And that's the challenge. There are some networks like Verizon actually filters further down. Like he might be up here and he'll filter down here. But that's harder for him to do, especially because he needs to know about the IP addresses of networks that are not connected directly to him.
So in the case of previously of the Pakistani Telecom, they are a provider, right? So
yeah.
As long as the provider kind of like colludes with you, then you could kind of get away with it, right?
I'm not sure about the collusion question. Let me answer a different part and then tell me if I'm being clear. So Pakistan Telecom has customers. So it has the right to announce prefixes that it doesn't actually, that aren't actually connected to its own network. right?
Right.
So actually, if you read the blogs of the operators, they were complaining. The provider of Pakistan Telecom was PCCW, and they didn't filter the announcements from Pakistan Telecom, and so everyone was sort of mad at this provider of Pakistan Telecom as well as Pakistan Telecom for doing things wrong. The challenge, though, is that this provider, Pakistan Telecom, could basically was sort of think about it here in the hierarchy, and it has some customers down here. He actually has the right to announce paths that are longer than 1, right, because he has customers. So this guy here would have to know exactly what prefixes are allowed to come out of him, which is kind of hard to know. Okay?
Right.
And what was the question about collusion?
Well, what I mean is, as if AT&T, well, if 20984 pays some money to AT&T and say AT&T just forget about so as long as AT&T works with them, then you can really stop it, and as the whole rule gets to propagate everywhere, but then that's a lot of filtering, right?
Yeah, so collusion is very hard to stop in these networks. The models that I'm more worried about is sort of rogue routers being taken over by rogue people and attacking that way. But if you start having networks actually colluding with each other, like in a cyber war situation, this is going to be hard to deal with. Right, so it's just very hard to deal with. Other things that people have proposed is multipath routing. So instead of sending traffic on one path, which is what happens today in the internet, send it through multiple different autonomous systems. These are currently research proposals, and the idea there is that if one of the paths is sort of going through somewhere it shouldn't be going through, at least there's some other path so it'll get to where it's going. Right, so but that's a completely different approach, and that's a really sort of far-reaching research idea. Is there anything? Other questions?
You mentioned earlier that the secure BGP may be slow, and have we done any performance evaluation on that part?
Okay, so secure BGP requires public key signatures for it to work. Public key signatures are inherently slower than symmetric cryptography, so SSL and things like that, they use symmetric encryption, which basically means that the sender and receiver share the same key that nobody else has, and then they can do the encryption really fast. Public key operations tend to be about 100 times slower. I may not be exactly right on this, so there are probably some crypto experts that can tell exactly what it is. But the bottom line is it is inherently a lot slower. So a lot of the times they use crypto accelerators, like hardware, to do this. That means you have to upgrade the routers. The other thing you can do is have a separate engine in your router. So you can have the router, and it processes the traffic in this processor, and it processes the routing announcements in another processor that's a little slower. Sorry, that's dedicated to routing announcements only. Routing announcements happen, let's say, every few seconds, whereas packets come every few nanoseconds. Right? So this processor has a lot more cycles to actually deal with these announcements. It can be dealt with. It's not a impossible thing at all. It's more an issue of actually upgrading the routers to do this. It's a little bit more money. It's technologically, I don't think it's infeasible. It's just more expensive. Yeah. And the expense is really the issue, right? So.
I think we have time for one more question, if anyone has one.
I'm not quite sure.
Sorry, we had a collision. Okay, go ahead.
I'm not quite sure I followed how secure BGP was working. So UPC is signing that it has a path to your destination. What's to stop 2984 from signing a message with its own key saying that it has a path to UPC?
Okay, I'm glad you asked this question. This means you were really paying attention. I glossed over that. It's in the protocol. Let me get to it very quickly. Okay. Here's how that works. Notice that the announcement that UPC is announcing actually has AT&T's name in it, in the announcement. So the announcement is not just UPC prefix, it's AT&T UPC prefix. That means that when AT&T makes its announcement, you have to look in the previous announcement and verify that AT&T's name is in there. He's authorized to use this announcement. So it's not just he's announcing downstream what he's doing, he's also putting the guy behind him's name. So I think what you were asking me, if I understood correctly, is why can't this guy just grab this, drop this thing off, and put his own announcement in? The reason he can't do that is because of this.
Okay, I was wondering what that was doing there.
Yeah, that's crucial. That's crucial to security.
So it's a point-to-point rather than a broadcast?
Yes.
Okay.
Which is another expense, right? Because now you have to sign for every edge that you're using, which is another reason the protocol is a little more expensive.
And send a separate message for every edge.
Right, exactly.
Okay,
yes.
Thanks.
Yes.
If you guys have follow-up questions, Sharon agreed to take questions out at the speaker's corner next to the Berlin Wall. And I think you said your booth was 217,
Yeah, I'm
right?
in 217, so please come by if you have any more questions. And if you know people who run the network or the security and can tell me what's going on, I would love to meet you. Okay, thank you.